In this section of chapter 3, we will discuss about moles-grams relationship, empirical formula, and molecular formula. First, I want to remind you how we express numbers, especially the big numbers. 1000, we often use the word 1000, but in our head, we have 1 followed by 3 zeros, or 10 cubed. When I talk about 1 million, it's 1 followed by 6 zeros. That's 10 to the power 6. Similarly, chemists deal with a lot bigger numbers, and we define it to be mole, which is also called Avogadro's number, which is given by 6.022 times 10 to the power 23. 1 mole of hydrogen atom means 6.022 times 10 to the power 23 hydrogen atoms. 1 mole of H2O molecules means 6.022 times 10 to the power 23 H2O molecules. So make sure you know that 1 mole means 6.022 times 10 to the power 23. I used to remember it like this, especially when I'm talking about mole-gram relationship. MGP, mole-gram periodic table. If I have a mole of carbon, by looking at periodic table, look under carbon in periodic table, you'll see this number, and that's the gram. So that means if I have 1 mole of carbon atoms, that would weigh 12.0107 gram, same as their atomic weight. If I have 1 mole of H2O molecules, then that is going to weigh the same as molecular weight expressed in gram. Molecular weight for H2O is about 18. 2 times 1 plus 16 for oxygen, and that gives 18. And this time your unit is going to be gram. So whenever you have mole of anything, you can convert that into gram if you know atomic weight or molecular weight of that substance. So that's why we have mole-gram periodic table. I mean, that way you know, whenever you need to know the conversion between mole and gram, look at periodic table. Now we're going to do number 34D, page 108. I'm sorry, page 107. This is page 107. Okay, the question is, how many oxygen atoms are there in 6.25? Let me write down those numbers. 6.25 times 10 to the negative 3 mole of AlNO3. Okay, so 6.25 times 10 to the power minus 3 mole AlNO3, aluminum nitrate. And make sure you first read the question so that you find out what is given and what you're supposed to calculate. Okay, number of oxygen atoms. So number of O atoms, that's what we're looking for. Let's see how we can do that. Start with what is given. 6.25 times 10 to the power minus 3 mole AlNO3 times, first I would like to get number of moles of oxygen atoms before I go to number. 1 mole AlNO3. Now look at how many oxygen we have. 3 times 3, there are 9 oxygen, because NO3 is in parentheses. That means it is repeated 3 times. So there are 9 oxygen. So 1 mole of AlNO3 molecules gives 9 mole oxygen atoms. 9 mole O atoms. I hope you understand that. Let me highlight that. So you multiply these two numbers in order to get 9. So 9 mole of O atoms. So what I can do is now mole would cancel out. Mole of aluminum nitrate, mole of aluminum nitrate would cancel out. Now next step would be mole of oxygen atoms, mole O, and the number. Remember mole number relationship, 6.022 times 10 to the power 23 oxygen atoms. Now let's write down the final step. 6.25 times 10 to the negative 3 times 9 times 6.022 times 23 O atoms. And make sure you complete this and get the final answer. Let's now go over number 39, A. Now glucose, C6H12O6. So they gave you the formula. So let's write down C6H12O6. That's the glucose. Contains 1.250. So you have 1.250 times 10 to the power 21 carbon atoms. So a sample of glucose has 1.250 times 10 to the power 21 carbon atoms. Now how many atoms of hydrogen does it contain? So basically you need to go from carbon to hydrogen by using this ratio in the molecular formula. So let's do it. Six carbon is equivalent to 12 hydrogen within that same formula. So when you have 6 carbon, there must be 12 hydrogen in order to get sugar. So that's what we're going to write down here. So 12 H atoms and 6 carbon atoms. So now we are going to cancel out carbon atoms. So basically you're multiplying by 2, which is 2.500 times 10 to the power 21, and the unit is H atoms. Okay, and that's part A. Let's now do part B. How many molecules of glucose does it contain? So this time we need to find out how many molecules. So let's do B. Again, I'm going to begin with 1.250. It's the same number, 1.250 times 10 to the power 21 carbon atoms. You can do one problem in more than one way. I'm just showing you one way of doing it. And now 6 carbon atoms are contained in one glucose molecule. So 6 carbon atoms are contained in one glucose molecule. So that would let me calculate the number of glucose molecules. So what I get is the following: 2.083 times 10 to the power 20 glucose molecule. Don't get confused between moles and molecules. Molecules is just label, and mole stands for number. Molecule means what kind of substance you're talking about. You're not talking about an atom, you're talking about a molecule. And mole means the number. The big number I mentioned to you is 6.022 times 10 to the power 23. Okay, now I'm done with part B. Let's do now part C. In part C of 39, they're asking for how many molecules of glucose does it contain. I think we did, I'm sorry, that's part B. Part C is how many moles of glucose does it contain. So in order to get moles of glucose, there's several ways we can do it. Let's start with glucose, number of glucose that we got in part B. 2.0, so I'm going to copy that number. 2.083 times 10 to the power 20 glucose molecule times, I want to get mole from number, 6.022 times 10 to the power 23. That makes a mole of glucose molecule. This gives me 3.460 times 10 to the power minus 4 mole glucose. We all have almost no space left for part D, but I can give you a hint so that you can do it. In part D, they're asking what is the mass of this sample in gram. So I know the mole of glucose, so basically we need to go from mole to gram. So mole to gram. So you start with 3.460. 3.460 times 10 to the power minus 4 mole of glucose times mole of glucose at the bottom. Let's not mix up with two different problems together. Now mole of glucose and gram of glucose. We are talking about a mole-gram relationship. Remember, MGP, mole-gram. Look at periodic table and add up masses. Keep in mind, this is C6H12O6. So add up masses, 6 carbon, 12 hydrogen, and 6 oxygen. And that is 180 gram per mole of glucose, and that gives 0.0623 gram glucose. Glucose is C6H12O6. In this slide, you're looking at relationship between empirical and molecular formula. Empirical formula is basically the minimum ratio of atoms in a molecule. So H2O2 is the molecular formula for hydrogen peroxide. Empirical formula for that would be HO, because the smallest ratio would be 1 and 1 in case of H2O2. However, in case of H2O, which is 2 and 1, because 2 hydrogen and 1 oxygen, you cannot go any smaller ratio than this. So it's going to remain 2 and 1. So empirical formula would be the same as molecular formula for H2O. So basically molecular formula would be a multiple of empirical formula. So I put down here empirical formula times n, where n could be 1, 2, 3, any of those numbers. It's not a fraction. It would be always whole number. Now here we're showing you one example. If molecular weight is 34, empirical formula weight is 17, So basically you divide molecular weight by empirical formula weight, and in this case that gives you 2. 34 by 17 is 2. That means molecular formula will be obtained by empirical formula times 2. So N is the multiplicative factor, and that gives H2O2. Let me go over number 51A. 51A, a composition of a compound is given which has 92.3% carbon. Percent is same as gram if I have 100 grams total sample. So let's use that. That would make life easier. So 92.3 gram carbon, and we have 7.7 gram hydrogen. Let's first try to get mole, because that's how you can get formula. Formula deals with number, not gram. So 12 gram of carbon, 12 gram carbon makes a mole of carbon, and that gives 7.69. That's mole of carbon. Starting with hydrogen, again I can get mole of hydrogen. So gram of hydrogen, mole of hydrogen. I'm rounding off these so it doesn't make a big difference. 1.0 mole hydrogen, and that's 1 gram of hydrogen. So this gives 7.7 mole hydrogen. Now we need to get empirical formula. For that we need to get a best ratio. Now at this point you'll have to select the smallest value. In this case 7.69 is the smallest value, and divide each of this number by 7.69. That's the method of getting empirical formula. The first number is 1, second number is 1.001. So that's pretty close to 1. So the fractional quantity is due to experimental error. So that basically has 1 carbon and 1 hydrogen. So empirical formula equals to CH, 1 carbon and 1 hydrogen. In order to get molecular formula, I need to get empirical formula weight. So empirical formula weight equals to 1 carbon plus 1 hydrogen, and you can look it up, these numbers in periodic table. Those are the bottom values. That means under the symbol carbon. Again I round it off. So 12 is for carbon and 1 for hydrogen, and that gives me 13. In order to get the multiplicative factor, remember empirical formula times N, that gives molecular formula. And I have molecular weight given in this problem. So molecular weight, let me write down here, or molar mass. Let me write down molecular weight, which is same as molar mass, equals to 104. So the multiplicative factor N equals to molecular weight 104, which is gram per mole, divided by empirical formula weight, which is 13, and that gives 8. That means I need to multiply empirical formula by 8. So my empirical formula is CH multiplied by 8, that's C8H8. So this is my molecular formula. So keep this in mind. From percent composition, first you get mole, and then you get the best ratio by dividing by the smallest number. If those numbers are close to a whole number, then round it off to a whole number. If it is say 1.5, then you don't round it off to 1 or 2. You just multiply by each number by 2, so that 1.5 becomes 3. And then you divide molecular weight or molar mass, 104, divided by empirical formula weight. That gives you the multiplicative factor, and then you multiply empirical formula by this number, to get molecular formula. Okay, let me now go over problem number 57. Now in this problem they gave you sodium carbonate Na2CO3 XH2O, that's with water molecule as part of this compound, 2.558 gram. When it's heated, water would be lost and you get anhydrous sodium carbonate, Na2CO3O. In other words, there'll be no H2O with Na2CO3. So this is going to be 0.948 gram. Now question is, what is the X value? Let's write down the question. Let me go over a similar problem just to give you an idea how we get this X value. One well-known compound is copper sulfate 5H2O. Question is, how do I get 5? If I have number of moles H2O on the top, moles copper sulfate on the bottom, what I'm going to get by looking at the formula, I would have 5 on the top, 1 on the bottom. Similarly, in this problem, if you divide moles of water, moles H2O, divide by moles Na2CO3, you're going to get X value. So keep that in mind, and we're going to do exactly the same thing. But the question is, how do I get moles of H2O? If I subtract 0.948 from 2.558 gram, that tells me how much water has lost from its original compound. So when you subtract that, you're going to get 1.61 gram H2O. 1.61 gram H2O. From gram of H2O, I can get mole of H2O. 18 gram H2O gives 1 mole H2O. And this gives me 8.94 times 10 to the negative 2 mole H2O. So I just got moles of H2O. Now I need to get mole of Na2CO3. Obviously I'll have to use 0.948 gram because that's the pure Na2CO3 without the H2O as part of the compound. So let's start with that. 0.948, that's gram, Na2CO3. Remember, how do I go from gram to mole? By looking at periodic table. So gram Na2CO3 mole Na2CO3. So you basically add up mass of 2 sodium, mass of 1 carbon, and mass of 3 hydrogen. And I rounded off pretty much all these masses. I get 106 gram. Even if you take more significant figures, it's not going to make a big difference. It'll be pretty close. So this gives me 8.94 times 10 to the power minus 3. So that's moles of sodium carbonate, mole Na2CO3. So now I have both the quantities. I have the number of moles of H2O in that compound, and also I have number of moles of sodium carbonate. So in order to get X, let's now do the calculation for X. X would be given by moles of water on the top 8.94 times 10 to the negative 2 on the top. On the bottom you have moles of sodium carbonate. 8.94 times 10 to the negative 3, and that's 10. So we got the answer. Our answer is x equals to 10. So let's highlight this. Hope you understood this. Here you're looking at a combustion analysis. If I want to know amount of carbon from amount of carbon dioxide produced in combustion reaction, then obviously from moles of carbon dioxide I can get mole of carbon, and then from mole of carbon I can get, of course, gram, or if I want to keep it at mole, just stop at that point. Similarly, if I want to know hydrogen, I can calculate hydrogen from mass of H2O produced in the reaction. Determining oxygen is a little tricky because oxygen comes from atmosphere, as well as oxygen could be part of that compound. So in that case, what you need to do is first get from mole of carbon to gram of carbon, and then mole of hydrogen to gram of hydrogen, and subtracting from the total mass of an object of the sample, you find out how much oxygen is actually there in the sample. Let's now go over problem number 81. Now I'm going to give you pretty much the steps of this calculation, and make sure you finish it. You now have the background to do this problem. So the reaction involves benzene, so let's write down that C6H6 plus Br2, that gives C6H5Br plus HBr. In part A, they're saying that when 30 gram of benzene, so A, 30.0 gram of benzene reacts with 65.0 gram of bromine, 65.0 gram of bromine, what is the theoretical yield of bromobenzene? Theoretical yield is nothing but calculated value. That means when this reaction happens, how much C6H5Br we would expect to get. So let me show you how we can do that. So start with, say, what is given to you, 30.0 gram of benzene. From there you can calculate mole of benzene. Remember gram mole, look at periodic table and add up masses of 6 carbon and 6 hydrogen. That would be gram of C6H6, that would give mole of C6H6. And then from mole of C6H6 you calculate mole of the product C6H5Br. Because question is asking about theoretical yield of C6H5Br. Now you start with Br2, 65.0 gram Br2. First you get mole of Br2. Again, gram mole relationship, make sure you get the weight from periodic table. Then from mole of Br2 you get mole of C6H5Br. Now you focus on these two quantities. The smaller value is the one that's going to form, because by the time you get the smaller value, you are going to run out of one of the chemicals, so there'll be no more reaction. That's why we always select the smaller value. Right now, without doing the problem, I do not know which one would be the smaller value, but make sure you figure out that. So that would give you the theoretical yield in mole. So from theoretical yield in mole, so let me show theoretical yield the smallest value. So in mole. Again, now you go from mole to gram of C6H5Br. And that's how you're going to get theoretical yield. Part B is asking for percent yield. They gave you the experimental yield. So it would be like experimental yield divided by theoretical yield times 100. That gives you percent yield. Hope you try yourself to do this problem. I also uploaded all these assigned problems in Angel and the solutions. Of course, this explains how to do it.